Let's see two simple examples of continuous function. So, claim the function f from R to R given by f of x equal to x is continuous, is continuous. Okay, how do we show this? So what we are going to do is fix x in R, or rather, to be ultra safe, fix x naught in R. We have to show that for each epsilon greater than 0, we can find delta greater than 0 such that if mod x minus x naught is less than delta, then mod f of x minus x naught is less than epsilon. Okay, I have written f of x minus x naught because f of x naught is actually just x naught. Now fix epsilon greater than 0 and set delta equal to epsilon. Okay, then mod x minus x naught is equal to mod f of x minus x naught, and this quantity is less than delta, which is equal to epsilon. So mod f of x minus x naught is less than epsilon, and we are done. That was fairly easy because the choice of epsilon was the choice of epsilon directly gave the choice of delta without any additional work. Okay, now slightly more complicated example, only slightly more. Consider f of x equals x squared. Okay, I want to claim this is also continuous at all points. Okay, so let me say continuous at all points. Now how do I show f of x equal to x squared is continuous at all points? Well, fix x naught in R again. Okay, and fix epsilon greater than 0. We must find a corresponding delta such that mod f of x minus f of x naught is less than epsilon. And for this appropriate choice, whenever mod x minus x naught is less than delta. Okay, we have to find that delta. Now how do we do this? Well, let's substitute what is happening. F of x is x squared and f of x naught is x naught squared. So this is, we have to somehow find out a delta such that x squared minus x naught squared will be less than epsilon. But x squared minus x naught squared, this I can write as x plus x naught into x minus x naught. Okay, into x minus x naught, the modulus of this. Okay, now suppose mod x minus x naught is less than epsilon. Suppose mod x minus x naught is less than epsilon. Then mod x is less than mod x naught plus epsilon. Okay, if mod x minus x naught is less than epsilon, we get that mod x is less than mod x naught plus epsilon. Now I make a statement. We may assume epsilon is less than 1. Why is this the case? Well, it's the exact same reason why in the definition of the limit of a sequence we need to consider only epsilon less than 1. think about this and tell me why. You need not satisfy this definition for all epsilon. It's sufficient if you satisfy for all epsilon less than some quantity. Well, the reason should be fairly obvious to you, even though I have posed it as a question. If you can get f of x to be epsilon close to f of y, you can certainly get it to be 10,000 close also, because 10,000 is greater than 1. Okay, so we may assume epsilon is less than 1. What does this tell us? It tells us that mod x is less than mod x naught plus 1. Okay, now coming back to this expression is nothing but mod x minus x naught into x plus x naught, modulus of x plus x naught, okay, which is less than or equal to epsilon times mod x plus mod x naught by triangle inequality, which is again less than or equal to epsilon times 2 mod x naught plus 1. I am just writing the fact that mod x is strictly less than mod x naught plus 1. So in fact I could have made this less than. Okay. Now we are done. We are done. Why are we done? I wanted to find a delta such that if mod x minus x naught is less than delta, then x modulus of x squared minus x naught squared should be less than epsilon. What we have done is, if we choose delta equal to epsilon, we find that mod x squared minus x naught squared is less than epsilon times 2 mod x naught plus 1. This is not what we want, right? We want it to be less than epsilon. But wait a minute. The k epsilon principle delivers the proof. That means for any fixed epsilon, if you can find a bound of the form mod x squared minus x naught squared is less than k epsilon, and this k is independent of epsilon, which indeed it is. That's why we assumed epsilon is less than 1, so that we have this independent. If you have this independent of epsilon, then this quantity x squared minus x naught squared can be made arbitrarily small. That was the k epsilon principle, right? Hence we are done. The k epsilon principle delivers the proof. So these are prototypes of how to write epsilon delta proofs. The prototype is as follows. Aim is to show, let me just, because it's an important topic, let me give it a subheading. Prototype for, rather I would use the word template. Template for writing epsilon delta proofs. Okay, fix epsilon greater than 0. Do scratch work to determine corresponding delta greater than 0 that would make the epsilon delta definition true. Then rigorously demonstrate this. So the key is you have to do some scratch work experimentation to find out what the corresponding delta is going to be. Okay, so you must always start such a proof by writing fix epsilon greater than 0. Then give an expression for delta in terms of epsilon. Sometimes it will turn out to be independent of epsilon also, even that can happen. Then rigorously demonstrate that the epsilon delta definition is indeed satisfied. This is a course on real analysis, and you have just watched the module on continuity of the functions x and x squared.